Okay, so this theorem tells us if a ray bisects an angle of a triangle, it divides the opposite side into segments that are proportional to the adjacent sides. The shortcut that we're going to use when we use it in proofs, this will be shown up in proofs, is going to be called the angle bisector theorem. And I will tell you what the angle bisector theorem does for us. So the angle bisector theorem tells us if I have a triangle, and in the triangle, one of the main vertex angles are being bisected. So here, do you see how in the given information I told you AC bisects BAD? Well, we know directly that a bisector, an angle bisector, takes a vertex angle and splits it into two equal angles, right? But now, if we have a triangle and there is a main vertex angle that's been bisected, that bisector actually splits the triangle proportionally. What do I mean when I say it splits the triangle proportionally? It means that I can say AB is to AD, AB is to AD as BC is to CD. So AB is to BC as AD is to CD. Right? And it really doesn't matter. So like I did left side over right side equals bottom part over bottom part. We can do left side over left bottom equals right side over right bottom. You know, there's so many different ways to represent the same proportion. At this point, we know that, right?
Right.
Thanks. All right, so how would we use this in an algebra problem? Let's look. So given VS bisects angle RVT, because we're bisecting angle RVT, that top angle by V gets split into two congruent angles. But now that VS, not only does it bisect that angle, it splits that triangle proportionally. What do I mean when I say it splits that triangle proportionally? It means that VR is to VT as RS is to ST. And we can now set a proportion. So I can do I could either do 8 over 10 or 8 over 4. It really doesn't matter. What do you want to do, 8 over 10 or 8 over 4? 8 over 4? I wrote 8 over 4 equals 10 over x. Why did I choose 8 over 4 versus 8 over 10? Because it's just an easier number. It's 2 over 1, right? Equals 10 over x. Cross multiply, we get 2x equals 10, so x is equal to 5. That's what the angle bisector theorem does for us. All right, so we are getting into proofs. The good thing is that after this chapter, we are taking a super long break from proofs. Chapter 9 is all about special right triangles, and then after chapter 9 is trigonometry. No proofs in either of those chapters. We'll briefly touch upon proofs in chapter 10, and then we're really done with proofs for the year after that. So we're coming to an end. So we will come back to number 4 and number 5 and number 6. We're going to come back to all of these, but I want you to go to where it's that blank sheet of paper that's there. There should have been another proof that I didn't, or I guess I didn't put in. So let's draw a proof. So I'm going to tell you that AB is not congruent. AB is parallel to DE. a second. I'm thinking. All right, I think this works out. We ready? Okay, so I'm telling you that AB is parallel to ED. And now I want to prove, doesn't this look like a proportion that's been cross-multiplied out? This looks like a proportion that's been cross-multiplied out. Anytime I want you to prove what looks like the cross-multiplication of a proportion, I need us to come up with a three-step game plan. It's a three-step game plan. So let's write out this three-step game plan. The last step, we're going to work backwards. The last step in our three-step game plan is the cross-multiplication. AC times ED equals AB times DC. That's the last step. The second step, we're working backwards in our three-step game plan, is to come up with the proportion that makes this cross multiplication. So if you remember, a proportion is the first over the second equals the third over the fourth, right? So when you cross multiply, the first is multiplied with the what? When you cross multiply, the first is multiplied with the fourth. Good. And the second is multiplied with the third. Do we agree? So now if we were going to put this back into a proportion, we're going to put our first, which is AC, over our second, which is AB, equals our third, which is DC, over our fourth, which is ED. So we're working backwards, three-step game plan. Okay, but now how do we get a proportion? Well, we need something that creates a proportion within the sides of a triangle. We have three different things now that gives us a proportion, gives us equal ratios within the sides of a triangle. The first one is similar triangles, or it could be side splitter, or now our newest one is angle bisector. So it'd be one of those, not all of them. So I should have put or. Are we ready? Okay, so now what we're going to do is step one, we have to create some kind of proof that these sides are within equal ratios of each other. So as of right now, is side splitter an option? Good. How do you know side splitter is not an option? Can someone tell me, looking at this diagram, how do I know side splitter is not an option? Repeat us.
Like the two triangles on top of each other?
Yeah, remember with side splitter, there has to be a line that connects to the two sides of the triangles and is parallel to the third side. So it always creates sort of a triangle within a triangle. Do you guys remember that? Does this fit the side splitter diagram? No. So this is definitely not side splitter. Side splitter's out. All right, is this an angle bisector? No, because none of the main vertex angles are being bisected, right? So angle bisector is out. So what do we have to do? Zia? Good, we're proving the triangles similar. How do we prove triangles to be similar?
Well, we can use all interior angles.
So the end game is usually like not side, side, side. Angle, angle. Good. So we are going to prove these triangles similar by angle, angle. Now, just to make sure these are actually sides of the triangle, it's saying we need AC is to AB as DC is to ED. So we're good. These are actually sides of the triangle, right? We're all good. So as long as I'm able to show that these triangles are similar by angle, then I can say their sides are in proportion. So Zia was on her way to tell us, how can we get angles congruent, Zia?
Alternate interior angles.
Good. Do we all see the Z? So I'm going to call this angle 1 and I'll call this angle 2. And I'm going to go ahead and I'm going to say angle 1's congruent to angle 2. Parallel lines yields alt interior angles congruent. Is there a Z on the other side too? Yeah. If I didn't want to do the Z on the other side, could I do vertical angles if I wanted to? Absolutely. I'm going to do the Z on the other side just so I don't have to make a new step. But you all could have done whatever you wanted. So in step number 2, I'm going to also put angle 3 congruent to angle 4 because it's the same reason. All right, so now do I have enough to say my triangles are similar? Absolutely. I'm going to go ahead and I'm going to say triangle ABC is similar to triangle DEC, angle, angle. Give myself some space over here. All right, now that the triangles are similar, that's check. Game plan 1, check mark. We're done. So now we go to game plan 2, step number 2. Now that the triangles are similar, can I say the sides are in proportion? Absolutely. So step number 4, I'm going to say that AC is to AB as DC is to ED. Here's a new step for you. Now, we spoke about this in the algebra problems, but we've never written it in a proof before. The reason, after we prove triangles similar, the reason we can say their sides are in proportion is going to be corresponding sides of similar triangles are proportional. So if you want to highlight, this is your new step that you'd have to memorize. And this works after you prove triangles similar if you want to say their sides are in proportion. Okay, so game plan number 2, check mark, we got it. So now that we have our proportion, aren't we always allowed to cross multiply proportions? So now I can go on and I can cross multiply and I can say that AC times ED is equal to AB times DC. And this one we had spoken about briefly, I think way back in the beginning of chapter 8. This was the means extremes product theorem. And if you guys remember, the extremes are spots 1 and 4. The means are spots 2 and 3. What does product mean? What operation? Multiplication. So what is it saying? Multiply the extremes 1 and 4, multiply the means 2 and 3. It's just saying you can cross multiply. That's all the means extremes product theorem tells us. You are allowed to cross multiply. And there we go. We did our proof. All right, let's do more proofs. Ready?
How many proofs will be on the test?
I don't know. I didn't make the test yet. Okay. So, looking at number 4, we have that angle 1 is congruent to angle 2. That's our given. Now, we want to prove the cross multiplication of something. When we prove the cross multiplication of something, how many steps do I want in my game plan? 3. Yep, I want 3 steps in my game plan. So if I want 3 steps in my game plan, let's come up with these. I'm going to go to my third step. We're working backwards, is our cross multiplication. Km times OP is equal to JK times MO. Right. Our second step is the proportion that gave us that cross multiplication. Remember, the proportion is the first over the second equals the third over the fourth. So when you cross multiply, remember the first is multiplied with the what? Fourth. And the second is multiplied with the third. So when we come to put it back into the proportion, we're going to say the first, which is Km, over the second, which is JK, equals the third, which is MO, over the fourth, which is OP. All right, now, what do we have to show before we can say the sides are in proportion? We have to show some proportionality theorem, right? What are our three theorems that creates proportions out of the sides in a triangles? We could do similar triangles. What else can we do? Good. Or angle bisect theorem. Or what's the last one? Or side splitter. You got it. It's going to be one of those, right? So now what I'm going to do, because there's a lot of triangles in this diagram, do you all agree? Let's see what sides we're even dealing with, and hopefully that will help us figure out which one of these we're going to do similar triangles, angle bisector, or side splitter. So it's saying KM is to JK as MO, MO is to OP. What is this highlighting a classic example of? Side splitter. Good job. This is classic example of side splitter. The thing is, we could only use side splitter if KO is what? To PJ. Parallel. We could only use side splitter if KO is parallel to PJ. But is KO parallel to PJ? Yes. Why? Because of the alt interior angles. Do we see that Z? So now step number 2, I'm going to go ahead and I'm going to say this. I'm going to say that KO is parallel to JP, and the reason is going to be alt interior angles congruent yields parallel lines. So now that I have that KO and PJ are parallel, now I can go to my game plan 1 and I can say side splitter. So the other ones are not our option here. So when I can say side splitter, I can go straight into the proportion. So KM over JK is equal to MO over OP. That is side splitter. And now that we have our proportion, can I cross multiply this proportion? Absolutely. So now we're going to have KM times OP equals JK times MO. Who remembers the reason for this, for cross multiplying? I guess you got it. Means extremes. Don't forget product. You need the word product. Theorem. Means extremes product theorem. Okay, one more proof. Anybody still copying this one down? Okay. So the only thing we're given in number 5 is angle 3 is congruent to angle 5. All right, we want to prove, let's highlight this, that RV is to VT as RS is to ST. All right, which one of our proportionality theorems is absolutely out? Which one's absolutely out, Sean?
Side splitter.
Yeah, side splitter. We don't have that line in the middle that's parallel, right? Side splitter is absolutely out. So that leaves similar triangles or angle bisector theorem. For similar triangles, we would need two angles, two pairs of angles. We can work with these markings up here and see what we can get to get one pair of angles. But is there anything else given to us to lead us to believe that we can ever get another pair of angles congruent? No. So what does that take? Angle, angle, similar triangles is out. So now we just are working with angle bisector. I have to show that angle RVT has been bisected by VS. If I'm going to show that VS is bisecting RVT, which two angles do I need to show congruent? Cam?
4 and 5.
You got it, 4 and 5. Right now, 3 is congruent to 5. But isn't 3 also congruent to 4? Yeah. So let's go ahead and say that. Angle 3 is congruent to angle 4. Vertical angles are congruent. So if 3 is congruent to 4 and 3 is also congruent to 5, what can we say? That 4 is congruent to 5. What reason? It's one word. Good, Lucas. You're bringing your A game today. Transitive. So now that 4 and 5 are congruent, I can now say that angle RVT has been bisected. What part of our diagram bisected angle RVT? See ya? Good. So step number 4, we're going to say segment VS bisects angle RVT. And the reason will be depth of bisect. So now that we showed that there's been a vertex angle in the triangle that's been bisected, can we say the sides are now split proportionally? Absolutely. Step number 5, I'm going to say that RV is to VT as RS is to ST, and that's going to be the angle bisector theorem. Can I go on to the next problem? Okay, there will be a question like this on your test. There will be a question like this on your test, so you want to make sure we know how to do this. BC is 9, AB is x minus 2, AE is 4, ED is x plus 3, BE is 5, and CD is y. We want to find the perimeter of ACD. Do we all agree in order to find the perimeter of ACD, I need to solve for x and y? All right, by a show of hands, how many people think, oh, sorry, there was one more. BE is parallel to CD. All right, how many people say we can use side splitter to solve for x? Yes, we can. How many people say no, we cannot? Good, you all win. We can absolutely use side splitter to solve for x. By a show of hands, how many people say we can use side splitter to solve for y? Raise your hand if you think, yes, we can use side splitter to solve for y. How many people say, no, we cannot use side splitter? Good, you all win again. Hey, if we can't use side splitter to solve for y, what are we going to use to solve for y? Victoria.
We're gonna plug in x and then use the like adding up the sides.
Good, what are we creating? Yeah. Proportion. Well, in order to create the proportion, what are we going to have to, what's leading us to that proportion? Because it's not side splitter. Yeah. Do you want to pass? Yeah. Steph?
A ratio.
A ratio? Well, that's what, like Victoria's saying, you're right. We want to create equal ratios, which is like a proportion, but what? It's not side splitter that we're using to create these equal ratios. Everpetus?
Like the similar.
Good. The similar triangles. We're going to use similar triangles to create this proportion, not the side splitter rules. So let's go ahead and we're going to say use side splitter to solve for x. All right, so if we're using side splitter, can somebody set up the proportion for me? Cam.
X minus 2 over 9 and 4 over x plus 2.
You got it. So now we have our proportion. So now we're going to cross multiply this proportion. So this is going to be x minus 2 times the quantity of x plus 3 equals 9 times 4. Right? Make your Algebra 1 teachers proud. Multiplying two binomials. How do I multiply two binomials? What is it called? FOIL or double distribute. FOIL or double distribute. So what does that mean? X times x is x squared. X times 3 is 3x. Now I'm going to double distribute the negative 2. Negative 2 times x is negative 2x. Negative 2 times 3 is a negative 6. That's going to equal 36. Combine our like terms. We are now at x squared, positive 3x, and a negative 2x. What does that give us? X minus 6 equals 36. What am I going to have to do to solve this? You're going to have to minus the 36 to set it equal to 0. Why? What are we doing? I think I heard it. Victoria, is that you? Good. We're going to have to factor. We're going to have to factor, and when we factor, it must equal 0. You cannot factor if it doesn't equal 0. So we're going to go ahead and we're going to subtract that 36. So now we're at x squared plus x minus 42 equals 0. So now I'm going to come up with my double set of parentheses. Somebody give me two numbers that multiply to a negative 42 and add to a positive 1. Lucas.
Positive 7 and negative 6.
You got it. Now we set each parenthesis equal to 0. So x plus 7 equals 0. X minus 6 equals 0. X equals negative 7, x equals 6. Are you allowed to have a negative value for x? Is that allowed?
Yes.
Absolutely, a negative value for x is allowed. What is not allowed?
Negative sides.
A negative side or a negative angle, right? So if I were to go back into my diagram and I plug negative 7 in for x, negative 7 plus 3, isn't that a negative 4? Is that allowed? No, you can't have a segment length that's negative. So for that reason, I am rejecting negative 7. So now we just have x is equal to 6. So now I'm going to go in and I'm going to plug in 6 minus 2 is 4. 6 plus 3 is 9. Are we ready to solve for y? Yes, we are now ready to solve for y. So now I'm going to say use similar triangles to solve for y. So we have 4, 4, 5. And now the bigger triangle. What's the left side of the bigger triangle?
13.
13. What's the right side of the bigger triangle? 13. So we're 13, 13, y. Can somebody set up a proportion for me? Thanks, Cam.
4 over 13 equals 5 over 1.
You got it. So here we're going to have 4y equals 65. Now, generally speaking, I would just leave it as 65 over 4. But ultimately, what am I asking you to find? The perimeter. And if I'm asking you to add, it's a lot easier to add decimals than it is to add improper fractions. So as long as that decimal is not a repeating decimal, we can change it to a decimal. So 65 over 4 becomes, did anybody do it?
16.25.
You got it, 16.25. Can we now find the perimeter of the big triangle? Yes, the perimeter is going to be 13 plus 13 plus 16.25. So the perimeter is 42.25. Okay, so your homework. Make sure when you do your homework, you look on Google Classroom, not this packet, because I took a few problems off. All right, so just check Google Classroom for the homework problems so you don't have to do them all. Okay, we're done for the day.